breakwaters in a controlled lab environment. So I'll talk about the stability of a typical New Zealand composite breakwater on the impact of a potential tsunami in New Zealand. And we'll see how a typical composite tsunami will perform on this, the breakwater will perform on the tsunamis. And we'll introduce a parameter to the design of breakwater to resist the tsunami attack. So tsunami is not rare in New Zealand. We've experienced several in the past several years. So but historical tsunamis, we've heard about extreme tsunamis like Indian Ocean tsunami in 2004, and also Great East Japan tsunami in 2011, which is a big one. So in New Zealand, we have a series of tsunamis from different sources, mainly earthquakes. So from this figure in the bottom left panel, we can see the infamous ring of fire, where most earthquakes and volcanoes occur along the state boundaries. So we can see in New Zealand, it's on the Pacific plate and the Australian plate boundary. And here is the ERI subduction zone, where the most significant earthquakes and tsunamis in New Zealand history occurred. So there are different sources of tsunamis. So when a disturbance to a water body like deep ocean or lakes disturbed by different sources, it can cause a tsunami, big or small. So the most common one is the earthquake, and also atmospheric pressure anomaly can also cause tsunami, which is called meteor tsunami, and landslides, both on the water landslide or landslide over land can cause tsunamis to lakes in the deep ocean. And also volcano eruption and the cascading effect can also cause tsunamis. The cascading effect like on water explosion, the pyroclastic density current, and also the caldera collapse or flat collapse can cause disturbance to the water and causing tsunami. And also the rare one, meteorites, can also cause tsunami. And the tsunami length can be very large, from several kilometers to several hundred kilometers. The period ranges from several minutes to more than 30 minutes. So let's look at a video from the 2011 Great Japan tsunami. tsunami was caused by earthquake in the ocean of the Japanese coast. And also, recent tsunamis in New Zealand. In 2016, the Breakwaters earthquake, which is in here, the center, not in the ocean, but on the land, also caused a small-scale tsunami in South Island, X Peninsula, especially in some V-shaped bays like Little Pigeon Bay. So this cottage is on the head of Little Pigeon Bay, which was damaged by the tsunami flow due to this event. So this tsunami was caused by the earthquake. Some evidence also suggests that the underwater landslide also contributed to this tsunami. This is the tsunami signal from the event, and we can see some turbulence to the tide level. And earlier this year, in 2022, the Tonga volcano eruption caused a global tsunami, and also that tsunami caused some damage in New Zealand, especially in Tutuaka. It's a small harbor. More than 10 ships were sunken, and the marine structure was damaged. Okay. So as I said, if a tsunami occurs, it can cause significant damage to coastal structures, like it can cause damage to seawalls, breakwaters, wharves, bridges, and buildings. It can transport several tons of buildings to several kilometers away. So it is important to know the potential damage to a structure, especially the important infrastructure, so that we can rescue the local residents. So today our topic is to investigate the tsunami damage to breakwaters. So in New Zealand, most breakwaters are sheltered by the geography, but some are not. For example, Napier Port breakwater. So Napier Port is run here, so it's facing the subduction zone, which is quite active, and tsunamis can occur. You never know, and we can see the Pacific plate is moving in that direction. So we chose that Napier Port breakwater as a case study. So that's the Napier Port and Napier Port breakwater. So it's facing the open ocean. So just a bit of introduction. Breakwater. So breakwater is a protective structure defending the harbour to keep the tranquility of the harbour. So it's usually designed to defend wind waves, but not extreme waves like tsunami waves. So it's important to know how the breakwater will behave on the extreme waves. So here's a survey of the structure of the Napier Port breakwater. So on the outer side, there is armor layer, in this case, the Echelon units, and so normally on the it can shelter some waves from the open ocean, and that's what it's designed for. So to investigate the stability of a breakwater on the tsunami attack, we'll need to construct a breakwater in a controlled environment. In this case, the experimental facility at the University of Auckland includes mechanics laboratory. So for experimental study, we cannot simulate tsunamis in the deep ocean because it's fast propagation speed, the deep ocean, and also its scale. But in the near coast, we can simulate the tsunami pulse and its impact to structures. So just a bit introduction to this facility. It's called tsunami flume or a dam break flume. So here is main channel, which is 19.2 meters long, 1.2 meters wide, and 1.2 meters deep. It's connected to a reservoir, which has a storage capacity of 30 cubic meters. So if the reservoir is filled with water and we lift the sluice gate quickly, and water will rush to the main channel, forming a dam break flow. And we use that dam break flow to simulate tsunami pulse. So how can we do that? I'll explain later. And here we have sluice gate and control system so that we can control the movement of the gate using computer software. So dam break flow and tsunami bore analogy. So this work by Chanson in 2006 facilitates our use of the dam break flow to simulate tsunami bores. So the idea is that they investigated the bore front celerity and free surface profile of a dam break flow and compare that bore front celerity and free surface profile with that measured from real tsunamis. And actually, quite a reasonable agreement was achieved. And we can say that we can use dam break flow to simulate tsunami bores. And the dam break flow, we can measure the Fruit number and compare that Fruit number to Fruit number in real tsunamis. If that agrees well, we can simulate the tsunami bore. Also, we need to make sure that this gate is lifted quite quickly. So first of all, we'll need to investigate the tsunami bore properties before we construct a breakwater in the flume. So we can change the reservoir water depth and also the gate opening height. So with different combinations, if we lift the gate for reasonably long, and we can generate different bores with different bore depths, propagation speeds, and also with different Fruit number. So the maximum bore depths can be 0.2 meters deep in the lab. So if we use a scale factor of 40, or we can get a 8.8 deep tsunami bore in reality. And the Fruit number in the quasi-steady stage is from 1 to 1.6, which compared well with real tsunami Fruit number. So the bore depth was measured using wave gauges, and the speed of the bore was measured using side-looking ADV. So if you look, you use ADV, you know that it's difficult to measure the velocity of the bore front because of the aeration and because of its being exposed to air initially. So for that bore tip propagation speed, we use some other method, which is distance divided by the time traveled through the distance. So let's look at the raw properties. We have a ball front and a quasi-steady stage following that ball front, where the ball depth is quite constant, as well as the through number. So after we get their properties, we can construct a breakwater, a scaled breakwater in the flume. So first of all, let's look at the layout of the Napier Port breakwater. So here is the cross section. This is the cross section we use in this study. You can see from this inset picture that in 1947, an earthquake occurred in here, quite close to Napier Port. It actually that caused a severe tsunami in Gisborne. So about the cross section, so the outer layer is the armor layer, the 13.6 ton Ekman units. Under that is on the layer 8-ton limestone rock, and behind that is crown concrete blocks and precast concrete blocks. So that's the image after construction. So I'll go to details of these units. Before that, we did some survey of the rocks and the Ekman units. So because our purpose is to investigate the stability of the breakwater. The breakwater consists of this units. For example, the Ekman units, limestone rocks, and concrete blocks. So we use fluid similarity, and the length scale is 40. The weight scale is different because we want to maintain the similarity of the stability between the lab and in reality. So this is crucial to keep that stability similarity. We have the stability number NS. So the idea is if we keep the stability number NS the same in the lab and in reality, we can keep that stability similarity. So the weight scale is this one. And these are the units. So the Ekman units, we make that using a technology called cavity injection molding. And for these rocks, I made them by myself, which is quite laborious work. Just look at that. It's laborious and it's difficult because we want to keep that density as well as the weight for a single block. So I made that in a container in the lab. So after construction, do a selfie. So as I said, the flume is 1.2 meters wide, and I focus on the central part of the structure because I want to avoid the wall effect as much as possible. So I dyed the Ekman units on both sides black, and in the middle I dyed different colors for the Ekman units so that I can track where the units are from. So the central part or the test section is 0.8 meters wide. Also labeled different numbers for different blocks behind that armor units. So I tested 4 different breakwater heights from 5 layers this blocks to 2 layers blocks, and expose these structures to a range of tsunami bore impact. So here's a video when the tsunami bore impact the structure. So the tsunami bore approached the structure, impacted over top the structure, and caused some damage. And we can see that the first damage is in the armor layer, and after the armor layer is destroyed, the underlayer will be extracted and transported to the inland area. And after that, these big blocks will be in danger and may be transported away by the tsunami flow. And we classify the impact phases in 4 stages. So the first one is the initial impact. The second one is splash up phase, and overtopping phase, and the quasi-steady overflow phase. And the major destruction is in this splash up phase and also this overtopping phase. And we observe that in quasi-steady overflow phase, the damage is small compared to these 2 phases. So now the problem becomes how to quantitatively analyze the damage to the breakwater so first we analyze the damage due to different bore height and different breakwater height. So horizontally is with increasing bore height, and as we can see that this increasing bore height or stronger bore, this damage is more significant, which is as expected. And horizontal, vertically from top to bottom is this increasing breakwater height. And so when breakwater height increases, the damage becomes smaller. And also we can observe that so first the damage occurs in the armor layer, and then the underlayer, and after that is the blocks behind the armor units. So we'll need to quantitatively analyze the damage, and we posed the parameter called FB. So FB is here. So it is the stabilizing strength divided by the destabilizing stress. So stabilizing strengths include the effect of breakwater height, HB, and relative density of the units, delta, and the size of the unit, dn50. And destabilizing strength is H0, which is the maximum depth of the tsunami bore. And we have 2 damage parameters from literature, the damage parameter S and the damage ratio RD. So this RD is simple. It's displaced number of units divided by the total number of units. And the damage parameter is the eroded area of the breakwater profile divided by the size dn50 squared. And we have empirical parameters to calculate the erosion area AE. So we have this FB, and we have two damage parameters. We can plot the damage of the armor layer in these two figures. So we can see that the horizontal axis is FB, vertical axis is S, which is the damage. So it links the damage and the parameters of the breakwater itself, and also the tsunami stress, in this case H0. So you can see when FB is 0.5 or smaller, total destruction occurs. And if FB is larger than 1.0, the damage is very small. So you can see the S is less than 3, and the displaced number or displaced percentage of the armor units is less than 10%. So these two figures are useful because it provides a guidance for us to design a breakwater that can resist a certain type of tsunami. For example, if we want to keep the breakwater stable under a certain tsunami, we can say we want to have the damage less than 10%, or less than 10% of the armor units will be displaced. We can use this one and find that value of FB. For example, FB is 1.0, and we can use this FB to link the breakwater property and the tsunami strength. For a given damage, say 10%, the tsunami depths will affect that damage, as well as the breakwater height, the armor unit size, so that we, if we have the 10% threshold, and we want to keep that threshold under, for example, 2 meters tsunami depth, and we can calculate the HB if we have a certain size of armor units. And there's some limitation to our research. It's applicable to a similar cross-section with similar interlocking among armor units. And in the future, we'll need to do more experiment with different breakwater profiles. And we can also use other parameters to quantify the damage to the armor layer, as well as the sheltered blocks. And at the last, I would like to acknowledge the University of Auckland Fluids Mechanics Laboratory, Natural Hazards Research Platform, and Napier Port Limited, and Opus New Zealand. So if you would like to get more information, you can look at this publication. And that's my presentation. Thank you.
So what? Sorry.
No, you go ahead, John.
I'm not sorry, no context whatsoever. So what sort of tsunami is the breakwater currently just able to withstand? Compared to, say, the last tsunami that occurred near Brisbane.
So do you mean the Napier Port breakwater? So let's look at this. So, so from this, so the H naught is the tsunami depth, the maximum tsunami depth, and the damage parameters are S and RD. So the current scenario is actually, let's see, it is the top, is the current breakwater scenario. So if you think that's acceptable damage, and so the corresponding tsunami depth is 156 millimeter in the layer. So times 40, the scale is the real tsunami depth.
Yeah, I have two questions. So first about the bore itself. So the range of fluid numbers you investigated, so it's from 1.05 to 1.6. So I would expect that you get angular bores sometimes, especially for the low fluid numbers. Did you observe angular bores? Breaking bores.
Yes, that's all breaking balls.
Even for 1.05?
Look at do you mean just?
Yeah, exactly.
Yeah, actually, that's all dam break flow. So it's a bit different from the wave breaking. So it can be seen as the bore after breaking.
And my second question was about the breakwater. Did you try different compaction of the granular material?
Yes, the compaction also affect the results, and we try to keep the same compaction in the study, and actually there's some variability in the results, and we use the average results in within the results.
Thank you.
Can you go to the damage ratio?
Damage threshold.
Yeah. No, damage ratio, the formula.
Yeah.
So the end displaced is just the armor unit.
Yes, that's only the armor layer.
So if the armor unit is completely destroyed, so there is no chance of it stopping anything.
Sorry?
If the core unit remains and the armor unit completely erodes, so you'll take it as complete failure. Like,
Sorry, I didn't get it. Did you mean if the armor layer is displaced?
eroded, and you are still left with the core unit, right?
Yes. So if that armor layer is or damaged, we call it destruction to the armor layer. In this results, we did not analyze the damage of the breakwater as a whole. The damage to the armor layer. Yeah, we can analyze the damage to the breakwater, like the underlayer and also the concrete blocks in the future.
So I guess I've got to, oh, sorry, now you have.
Just another question about the armor units. So you only try like with the cube ones. What about the other shapes? Like there are kind of the new ones can lock each other and shape a very strong armor layer. So
Yes,
it'll be different, I guess.
yes. That's should be different. So that's the limitation of our work. Our work is the limitation is to for a similar profile with similar interlocking between the armor layer. Yeah, so if that armor layer, the units are well interlocked, it should be stronger in terms of the resistance to tsunami impact.
It's like new harbors using different type of armor units these days. So like it could be very, very different, the result. Like
Yes, it's probably a bit different. Yeah.
Only done one PhD, Zhonghou.
In this case, the interlocking is called the random layout of the armor layer. So they can be uniform interlocked. Yeah. Because in the Napier port case, it's randomly placed.
So I get the questions, but mine are more from stupidity. So if you show a picture of the damage parameter again, that one, perfect. So that top graph, so the bottom one looks pretty nice, right? Everything's kind of collapsed onto more or less one line. Something, I guess if you knew, you probably would have done it. So there must be something missing that's stopping those top figures from kind of collapsing down onto one line. You could feel what that might be. That could be something like the compaction or something.
Yeah, that's a good question. Yeah, that's why we use different damage parameters, and also actually we also use another parameters different to FE as the horizontal axis, and in that results it's not even as better as this one.
Okay.
Yeah,
It's pretty good.
yeah,
Just something that you're missing. That
yes, there can be many more variabilities related, but I don't know.
Yeah, it's non-trivial.
Okay.
I guess my other question is thinking about, in terms of as the tsunami comes in, it's obviously shoaled up to make these undulate boards. Is that, I haven't got a good feel for what the bathymetry is like beyond the breakwater. Is it, would it already shoal or is it really deep? So I guess your point of impact is the scaling right for that. That's kind of my question in terms of how the tsunami shoaled to get to the breakwater.
Oh yeah, that's a very good question. So for some tsunamis, before the largest wave, there will be a recession in the water, and it will expose the breakwater to maybe to the surface, and we made some assumption that so before the impact it's dry and yeah, that's the assumption. And actually some other breakwaters are in like the muddy flat area. It can be exposed to I guess what I'm trying to say is that we use dry bed initial condition, mainly because of the recession of the first wave impact of the tsunami.
No, you're right, mate. It would have started to shoal before it even got to the breakwater. Because I'm thinking, if it was particularly deep water, it just washed straight over the top, wouldn't do anything. So interesting. There must be a nice balance between the depth at which you put your breakwater for it to actually be useful.
And yeah, I have one more question. Have you considered the condition of the several tsunami boards? Because usually in reality, there might be 4, 5, or 6 tsunami boards in a group. So that's possible that the second tsunami board will hit the breakwater when the first one has not ended yet. So there might be some overlap So how would you consider that effect?
We didn't consider a second ball.
How do you think that could influence the stability of the breakwater?
So I guess the most severe damage will be caused by the largest tsunami wave. So, for example, a train of tsunami waves propagate to the coast, and the damage will be the most significant damage will be caused by the most extreme tsunami ball, and the preceding damage. That's a cumulative effect. If the preceding tsunami ball will damage to the breakwater, that also will affect the damage.
So the first of all will be the extreme ball you just said.
No. The first wave can be the most severe, the largest wave, but in most cases it's not. In some cases, the second wave or the third can be the largest.
Can I ask why? Why is the second or the third could have been the largest rather than the first? If you decide on the tsunami.
I think that's because of the generation mechanism of tsunamis. So because for example, if an earthquake is the source, the movement of the ground will have disturbance to the sea surface that might cause the first wave being not the largest. I'm not sure.
Can't we just extrapolate this result to that? So we can assume the first one does erode some armor layer, then we can use the second one as a single wave, which erodes from here. So can't we just extrapolate these results to a train instead of considering a train? So the first wave comes, maybe it does 60%, some 20% erosion. Then you consider the eroded one as the breakwater. Then you consider the next wave. Then like that. We can just extrapolate this, right?
Unless there's interaction between the receding first wave that then interacts with the propagating second.
This like the backward bore follow from the first one and then goes to the second one, and the backward bore follow from the second one to the third one. So it kind of damped the other one. Maybe the first one is not this strongest, but maybe the second or third, I don't know. But after a while, going to damp the rest because of the backward bore follows from the first ones. And also the heights of water are changing after a while. So the difference, the high difference is going to be decreased. So the destructive power of the after like 4 or 5 waves are going to be much less than the first ones, I guess.
So
Thank you for the comments.
do you think it's viable to reproduce those interactions between the balls using computer models like you have used in NIWA? Is that possible? Because there might be several. The first ball may have some reflection from the water and interact with the other balls, and that might cause a very complicated wave building from the water.
Yeah, and in terms of computer modeling, they're very some advanced numerical modeling. I guess SPH can do this. Interaction between the tsunami ball and the structure, and another called SPH-DEM can also simulate that, which is quite computationally expensive. I'm not an expert in that. I don't know.
Yeah, the Darfur groups that they did it, but like it not for like a complete harbor, just like a mimics of harbors, like a single obstacle or just few of obstacles. They use numerical modeling for dam break, and also the continuous type of the waves for that. But for a larger scale, looking the real size is very high computational one. But for a small ones, they already did the numerical simulation. Some group from Santa Barbara University, I guess, and some other group, different part.
Just one more, just the last one. Just sorry, I'm not too. Is that just okay to increase the height of the breakwater, to defend against the tsunami? So do we need to consider other factors? If we have that money, can we just simply increase the height so that'd be safe, right?
Yes, but it will be expensive. So actually, the height can be interpreted as the height above water. So if you have a breakwater that's much higher, that will cost a lot more money.
You need to increase the as well.
And also,
What would that be a transit, right?
and also you need to have a balance between the cost of breakwater and also the risk of a tsunami and what size of tsunami you will be exposed to. Balance.
Yeah, so I have a completely dumb question. Right? So my understanding is that breakwater is designed to essentially break wind-driven waves up, right? And if you can deal with tidal waves, it's a bonus, but it's not the primary design. And most of the damage from tsunami is not so much the height of a tsunami, even though we focus on that, but the sheer volume of water from the tsunami, right? That then basically comes into a place where there's normally no water displacing air, right, and causing damage. And so if the breakwater is not high enough to actually stop tsunami from coming in, right, then how much benefit does the breakwater really provide in the event of a tsunami? I can imagine that because if the water makes it over the top of the breakwater, it's still creating damage on land. I mean, does the breakwater slow the water down, the progression of the wave down, or is it just about reducing the initial impact wave, the height of the initial impact wave? Because to me, it's only a minor contributor to the damage caused by tsunami.
Yes. It will reduce the impact of the sheltered area, and it will slow the tsunami quite not too much, but a little bit.
And that breakwater will be built at the seaside of the harbor, right? And I think we still have some seawalls at the other side of the harbor to defend against the waves. Is that true? There's actually kind of the two layers of the protection when the tsunami over the first layer of the breakwater. We have impact on another kind of the seawall. That's my understanding.
What you really need is a good kilometre or so of mangroves.
I mean, we're ever evolved to deal with tsunamis, right? These are really rare events that evolution simply, landscape evolution and biological evolution simply isn't equipped to deal with, because there's no way of selecting an optimal structure. But you're right, mangroves are effective because it's basically creating drag the whole time.
Yeah, and actually the hard protective structures are expensive to protect tsunamis, and that's why we need soft measures like regular drills to teach people where to go to higher land, and to build some robust structures to serve as a protective structure from the tsunamis.
In the long term, we're to build, right? The Japanese, the tsunami stuff, because they learned after several tsunamis, the only way you can deal with it is to not build with it below its life.
Yes. And in Tauranga, they have regular drills to help people evacuate to the safe routes if the tsunami is too aggressive.
So if you live in Papua,
Warning systems. I mean, they only had in that Japanese tsunami, they had about half an hour, so that was the real issue. It didn't trigger some of the warnings because it wasn't long enough. Some amount of shaking wasn't long enough, so it didn't trigger the warnings. So
I think
basically just
Tauranga cannot be used as a good example for anything. Coastal risks. They on all coastal risks.
we are recording this. That's
all right.
gonna
It's true. Why are we expanding Papua more when it's flat as a pancake, right? Not even tsunami, just a tidal wave making across the area. Then you have a giant swimming.
Any more questions?
Good discussion.
Okay. Okay. Thank you very much.
Thank you. Thank you for your attendance and thanks for all the comments and questions. Yeah. Thank you. Thank you. Thank you.
I would not say what we really think of how
Very well. Tauranga is the Florida